Your expert is James F.P. Cotter, a professor of geology at the University of Minnesota, Morris. An award-winning educator and mentor, he has published more than 20 papers and 90 abstracts on glacial geology and has received several National Science Foundation grants.
Practical geology is geology that everyone should know to understand the natural world around us. It's a subject that invites questions. I found this interesting rock. When I was traveling this summer, I saw this strange landform. I've always wanted to learn more about glaciers. Where should I go? But what is practical geology? That's a great question, and one that I've spent a lot of my career as a geologic educator wrestling with. After all, there aren't a lot of books out there titled Practical Geology. So here is what I think you should know right up front. First, you should know how to see geology. Learning about the Earth should be participatory. Like recognizing trees or birds, being able to identify geologic features and different rock types will help you understand and appreciate the world around you. For example, here's a sample that has been sliced flat with a slab saw. We look for lines. Can you see them here? You can see them even more clearly when it's been polished. This rock immediately shows you two things. The lines show you there are layers. Second, the lines have a bend in them, so the layers are deformed. That's seeing geology. Whenever you're outside or traveling in a car, knowing geology will allow you to see and understand things you never have before. John McPhee, the author of many books about geology, wrote, "Rocks are records of events that took place at the time the rocks formed. They're books. They have a different vocabulary, a different alphabet, but you learn how to read them." For another example, let's take the word texture, which is used frequently in geology. Granite is a common rock with a texture where all the crystals that make up the rock are all about the same size. Moreover, it's a size where all the grains are also clearly identifiable with the naked eye. In fact, the word granite comes from the Latin word granum, or grain. So granite has a lot of visible grains that are the same size. Granite forms directly from a liquid, a magma deep in the earth. So granite is called an igneous rock. In fact, granite is the most common igneous rock found on most of the Earth's dry land surface. I have some examples of rocks that are called granite by the industry. But which ones really are granite? This is a granite. Granite has a few types of ingredients. You can see the mineral quartz is gray. Granite has feldspar, or maybe two. This sample has two feldspars. Here, the feldspar is white, and here, the feldspar is pink. Last, granite has some darker minerals, like this biotite here. These have iron in them. How about this one? Pretty similar. The grains are smaller. This is a granite. But much of the granite sold for countertops isn't really a granite in the geologic sense. How about this one? It has the same minerals as the two granites. Maybe this rock started as a granite, but here, those same minerals are grouped together or banded. That's a change of form. See the bands? Dark minerals, the pink feldspars, and more dark minerals. This is a metamorphic rock, not a granite. Igneous rock, like granite, is much more uniform. Now, one more. Look at the sample. Is this a granite or not? It's got the dark biotite. It's got the light-colored quartz, but nothing in between. No pink or blue feldspar. This was sold as granite in Vermont, the so-called Granite State. In fact, the Vermont legislature back in 1991 declared that all igneous rocks of Vermont are to be considered granite. The next time you see a countertop that might be granite, see if it contains quartz, feldspar, and a dark mineral, all about the same size, and whether there is a uniform absence of some larger structure or pattern. So practical geology means learning to see geology, but it also means being able to make discoveries yourself. You can. You probably won't get rich, but you can certainly do many types of exploration and collection safely and legally, and it makes a great hobby. What to try depends on where you are. If you're near the mountains, looking for gemstones and minerals is a great way to learn geology. If you're near the non-mountainous part of the country, try collecting fossils. Fossils can be found in more locations than you think, from road cuts to riverbeds to construction sites. Most fossils that I find are the same fossils anyone can find. Here's a brachiopod-rich rock from southern Minnesota. Brachiopods are very ancient animals that lived in the sea. Very few species remain today. They have two valves that are usually different shapes. In Minnesota, they are a very good indicator that you are in rocks over 400 million years old. Many states have a state fossil. In Kentucky, brachiopods are abundant and they became the state fossil. A state fossil receives this designation because it is abundant or because it's unique. The Nebraska state fossil, on the other hand, is a mammoth tooth like this one. This is a very difficult fossil to find. You probably need a guide to recover one. A quick search in local field guides will help you identify a fossil and reveal the age of the rock that it's in. Practical geology also means gaining an understanding and appreciation of geologic processes. What are geologic processes? They're anything that impact earth materials and landforms. Many geologic processes transport and erode earth materials. Think of rivers, wind, waves, glaciers. Also, earthquakes and volcanic eruptions change the landscape. Together, these processes shape some of the landscapes we see and the resources we use. These same processes are also potential sources of damage or harm. Floods, for example, are a very normal geologic process, and in some cases, they are critical to maintaining river ecology. However, floods account for the largest number of major disasters in the United States on an annual basis. Understanding geologic processes is critical to ensuring your safety. Beyond processes, practical geology is also about geologic resources. Things like gold, minerals, gems, water, petroleum. There's an old saying in geology: everything produced is either grown or extracted. That means if an object you own or use is not plant-based, then it has a geologic origin. So anything with metal, plastic, sheetrock, or concrete started as a geologic resource. There's also your health. What could be more practical than how geologic materials improve or negatively affect your health? Fluoride is added to most water systems, and it's part of the common mineral called fluorite, found in Colorado granite. Dissolved in water, it can make stronger teeth. Though watch out, too much fluoride can cause mottled teeth. I am absolutely convinced that geology and geologic processes affect most people on a daily basis. I am also convinced that geology is a great science and a lot of fun to learn about and actually do. And I'm completely unbiased. Once you're able to read the rocks, as McPhee puts it, and to understand the geology around you, you'll be surprised by how you also learn to see changes in the geologic world over time. For example, mountain ranges that would rival the Alps or the Himalayas once existed in several places in the US, including Minnesota, where I teach, and in my home state of New York. The rocks in and around Chicago were part of a coral reef formed at the time the U.S. was at the equator. At about the same time, beautiful, warm, shallow seas in Kansas and Michigan existed for millions of years. But those seas later dried up and left behind the salt many people in the U.S. season their food with. And what is now Florida was once part of South America and was joined to Georgia when the Atlantic Ocean first formed. During an 1875 geologic survey of the Colorado River, John Wesley Powell, the famous geologist and adventurer, wrote as he descended into the Grand Canyon, "All about me are interesting geologic records. The book is open and I read as I run." So how do you learn to read the rock record and interpret the geologic world? Keeping an open mind helps. Finding dependable resources to learn from is also important. Resources such as geology textbooks, refereed journal articles, or articles in popular literature that cite refereed journals. And of course, an inquisitive mind and passion for learning are irreplaceable. There are also three key concepts that I believe make learning and enjoying geology possible. These are: 1, the understanding that the Earth's surface is always in motion. 2, the concept of deep time. And 3, the reality that everything on Earth, the oceans, the atmosphere, the climate, and the organisms, change through time. If I can teach you those three concepts, I think I can open your mind and imagination to learn practical geology. Let's talk about the first one. The Earth's surface is in motion. So I do research in Brazil, and over the 2.5 decades I've been to Brazil more than 20 times and conducted research in 8 separate states. When I tell people I'm going to do research on glacial geology of Brazil, they always question what it is I do, and with good reason. People always say they've seen images of Brazil and they have never seen pictures of glaciers. In fact, it's quite the opposite. To most people, Brazil is a place of warm beaches and beachgoers dressed in something very different than clothes you might expect in a glacial climate. But what I study are the geologic glacial materials left behind by a long-ago glacier in the south of Brazil, from 300 million years ago. Now, when we study the geology in this area, my students and I regularly come across pieces of petrified wood. This is a glacial deposit. It's accumulation of sedimentary rocks. Here's one rock here. Here's another one. And here's the petrified wood. There are two important things about this petrified wood. First, it was petrified, that is, turned into a rock, before the glacier incorporated it into its sediment load. Glaciers usually crush wood. And 2, the petrified wood was transported by the glacier to the south of Brazil and then deposited. When I first asked my Brazilian colleagues where the wood was coming from, they simply said, Africa. The wood came from a forest that grew in Africa millions of years prior to the glaciers forming. When the glaciers did form, roughly 300 million years ago, the glaciers then eroded the rocks that originally contained the wood and carried it to Brazil. Once I tell my students about this, they are always on the hunt for petrified wood from Africa. So how can it be that Brazil once had glaciers? And how did those glaciers transport wood from Africa? This phenomenon is the result of the Earth's surface in flux, both from Earth's internal and external forces. Internal forces are the result of the remarkable process called plate tectonics. The basic concept of plate tectonics are straightforward. The outermost layers of the Earth's rocks, called the lithosphere, is made up of enormous pieces called plates. There are 8 main plates, like the North American plate and the Pacific plate, and a bunch of smaller ones called microplates, like the 5 microplates that make up the west coast of the U.S. Each of these plates and microplates of lithosphere essentially ride on top of the asthenosphere as it moves. This motion is called convection because, like convection ovens say, the motion is driven by warm, less dense material rising and cool, denser material sinking. Finally, for the most part, tectonic events, the building of mountains, the creation of deep ocean trenches, the formation of oceans, occur at plate boundaries. The reason I find glacial deposits in Brazil is because at one time what is now called Brazil was part of an even larger lithospheric plate that was at the South Pole. That larger plate is called the Gondwana supercontinent, a plate boundary formed between the pieces we now call Africa and South America, and in that boundary an ocean formed, becoming the South Atlantic Ocean. How long did it take Brazil to get where it is today? A long time. Plates move about 2 to 3 centimeters per year. That's about the rate that fingernails grow. Have you ever seen those people with the freaky long fingernails? In the time it took to grow those nails, the tectonic plate they are living on, say the North American plate, has moved about that same length. It's strange to think about, but in, say, 74 years or so, which is the average American lifespan, North America will move a little over 6 feet, which is close to the average American height. So the lithosphere, the surface of the planet, is in a constant state of flux associated with plate tectonics. So what about the other contributor to the Earth's surface in motion? External forces. Those forces also in part resulted in the piece of petrified wood buried in Africa ending up in Brazil. Most of the discussion of the external forces that continually affect the Earth's surface are really about the presence of water on Earth. As we all know, water is a second major thing that makes our planet so incredibly special. It's in middle school where kids are introduced to the water cycle. It's also known as the hydrologic cycle. The concept is usually taught in the context of all Earth's waters being connected. Atmospheric water falls as rain or snow and becomes surface water. Surface water is either temporarily stored in lakes or glaciers, for example, or infiltrates into the ground or runs off as rivers and streams. At any point, surface water can be evaporated or transpired by plants back into the atmosphere. The hydrologic cycle taught in school usually closes with rivers entering the ocean and the ocean evaporating most of the water in the hydrologic cycle back into the atmosphere. As a result, all waters are connected. But the water cycle is not just about water. From the standpoint of anyone interested in geologic processes, the hydrologic cycle is what generates many of the external forces that influence the surface of our planet. Compare this with the other planets of the solar system, or even the moon. The moon has a cratered surface and looks nothing like the Earth, yet the Earth has been hit by a large number of meteorites. On the moon, there are over 1 million impact craters bigger than 1 kilometer across, and over 5,000 that are more than 20 kilometers across. By contrast, on Earth, there are only 190 confirmed impact craters. While most of Earth's craters just don't have a well-preserved form. Why the difference? External processes in the form of running water, glaciers, landslides, and the formation of soil over time erase meteor craters or volcanic flows that remain so clearly visible on the moon today. Our planet looks youthful compared to other planetary bodies because of those external forces that are closely tied to the hydrologic cycle. So my petrified wood in Brazil, what is now South Africa, was located at the South Pole. precipitation fell as snow, accumulated and formed a glacier. That glacier, under the influence of gravity, flowed northward, eroding the rocks underneath it and transporting petrified wood to its margin, which is now located in what is now South Brazil. So the Earth's surface is in a constant state of change. Internal forces that cause plate tectonics result in the formation of mountain ranges. External forces, such as rivers, glaciers, and landslides, wear away those mountain ranges and keep our Earth's surface in flux. It's also important to understand the impact of humans as a geologic process. If you take all the geologic processes I just mentioned and totaled up all the land surface material they transfer every year, it would not make up 10% of the land surface material that humans move. Cumulatively, or in particular cases, some of this human activity causes problems. Deep geologic time is another important concept I want you to grasp. As a professor in a public land-grant institution, I enjoy many opportunities to interact with the public. The University of Minnesota-Morris is a resource for the people of Western Minnesota. Because the area is predominantly agricultural, I have met a lot of people who spend time in the field and have questions about the land, water, and rocks. I see a lot of fieldstone that people wonder about and want to know about. People also bring in fossils, rocks with odd coloration, minerals, and ore, and even occasional human-made materials that look like rocks. Here are rocks that people wonder about. This is a coral from the bedrock near Winnipeg. Frequently, I'm asked if it is a human brain. These two rocks are sedimentary rocks from the Belcher Islands in Canada. The holes form naturally, but people ask if it was made by Native Americans. Banded iron formation is found in many places in Minnesota. People wonder if it's a meteorite. When I explain to people what they found, how it ended up in their field, and how old it is, almost always they will say, "Whoa, that's really old." But to a geologist, that's not all that old. When I mentioned that the most recent North American glacier carried the rock and deposited it in their field around 20,000 years ago, that too seems like a long time ago. But geologically, that happened a geologic instant ago. The age of the Earth and geologic time have interested people as long as people have been writing. Yet the concept of billions of years of history is really difficult to grasp. It doesn't help that popular media has dinosaurs and woolly mammoths cavorting together. Those animals lived 60 million years apart and certainly never cavorted. Starting in the 1980s and increasing in the 21st century, geologic educators have made an effort to increase the appreciation of geologic time by using the phrase deep time. During the space race, 2 decades earlier, the concept of deep space was introduced to increase the perception of the dimensions of space, and it worked. The hope was that deep time would increase the perception of geologic time. It's an educational experiment that is still ongoing. So what's there to know? Most importantly, the Earth is 4.6 billion years old. And the oldest rocks found are about 4 billion years old. I showed you the Morton Gneiss from Minnesota. It is the oldest lithosphere in the United States, and it's 3.5 billion years old. Rocks that are about 1 billion years old sometimes contain fossils of single-cell organisms, but abundant fossils and the abundant life that left those fossils behind didn't appear in the geologic record until 0.6 billion or 600 million years ago. Dinosaurs first appear in the geologic record at around 226 million years ago and then go extinct 66 million years ago. The last ice age started about 1.6 million years ago and continued with glacial retreats and advances up until the last glacial retreat about 10,000 years ago. But in the end, it all just becomes numbers, right? Therein lies the difficulty of grasping deep time. There are analogies that people use to get the point across. Say we take the entire history of the planet, 4.6 billion years, and make it equal to a single calendar year. So January 1st of our year is when the Earth formed 4.6 billion years ago. This year then would go from January through September with no record of life at all. In this geologic calendar year, abundant life is established on Earth in November. These are rocks of the Cambrian period. The dinosaurs appear and then go extinct in the month of December. That extinction event occurs at the end of the Cretaceous period. And the last ice age, which occurred during the Quaternary period, ended in the last minute of December 31st. All of written history would be equal to the last few seconds of that geologic calendar year. Mark Twain equated geologic time with the height of the Eiffel Tower and correctly estimated that all of human history was equivalent to the thickness of the paint at the top. Human history makes up very little of the history of this planet. So why is it important that you understand geologic time? If you understand geologic time, you can begin to understand how truly dynamic the Earth is and how profoundly the internal and external forces of the Earth are changing the Earth around you. Niagara Falls began to form about 12,000 years ago at the end of the last ice age. And in just 10,000 years from now, unless engineers intervene, Niagara Falls will erode back and Lake Erie will drain. Or consider the San Andreas Fault in California. It's moving. The San Andreas is the boundary between the North American and Pacific plates. At the present rate of movement, Los Angeles will be next to San Francisco in 35 million years. Whoa. There is a constant dynamic. In 10 million years, a new Hawaiian island will form as the result of volcanic activity. Meanwhile, the oldest one or two islands in the chain will erode below sea level. But how do you actually determine the age of the Earth and the Earth's features? People always ask me, are the dating techniques accurate? The short answer is yes, dating techniques are accurate. And the reason is that the principle of dating techniques is very straightforward and that multiple techniques are used as cross-references. From the earliest times, people have wondered how old the Earth is. The ancient Greek writer Herodotus tried to determine the age of the Earth by determining the amount of sand that was added each year to the delta being built where the Nile River enters into the Mediterranean Sea. He multiplied this rate by the total volume of the delta. His estimate, several thousands of years. But what he didn't realize is that the sand is not only being added, sand is also being removed from the delta by storms. In the later 19th century, another famous attempt to estimate the age of the Earth was made by Lord Kelvin. He assumed the Earth was molten at its formation. Again, a true assumption. He took the heat of a massive liquid rock the size of the Earth and then multiplied that by the cooling rate that would result in the present temperature of the Earth. Again, this is absolutely brilliant. His estimate, 40 million years or maybe as much as 100 million. What he didn't know is that the Earth has an internal heat source, so its age calculation came out too young. That heat source goes back to the discussion of plate tectonics, which he did not know about. So there's heat from the accretion of the planet, heat due to friction, and there's also heat from radioactive decay, which he also didn't know about. Modern methods employ the same principle of rate times the volume, but now radioactive elements are included. Radioactive elements are unstable, and some break down or decay at a constant rate into a more stable daughter product. Radiometric dating techniques use the rate of decay times the volume of the daughter product to provide an age. It is an amazing technology. There's another way to read the rocks. It's called relative age dating, the determination of a sequence of events. Many places you will visit will have multiple rock types. How can you determine which formed first? One possible clue, you may notice that some of the rocks are inside other rocks, a solid within a solid. Let's look one more time at my petrified wood. Now, the rock that contains the piece of petrified wood is solid, and the petrified wood is also solid. Is there any way that piece of wood could be placed into a solid rock? The answer is no. The solid piece of wood was picked up by a glacier and deposited into the soft material around it. After millions of years, the material turned into rock. We say it lithified. The wood formed first, and then the rock that contains it was formed later. That's called relative age dating. So just by observing a solid piece of rock, like this granite here, or this petrified wood here, when they're contained within another rock, you have some idea of the sequence of the formation of geologic units. The third important thing I want you to understand is that everything changes. You're beginning to get it, right? You take geologic processes, both internal and external, and you let those processes occur on a scale of deep time. And interesting things happen. The rocks, fossils, and landscapes around you will help you figure out what those interesting things are. Say you're in the eastern part of the United States 20,000 years ago, which is a short while ago in terms of deep time. Glaciation was in full swing. From New York and New Jersey northward, a glacier that was at least a mile thick covered the entire landscape. There's a ridge called the terminal moraine that marks the southern limit of glaciation. A lot of times, you can identify these moraines by the presence of lakes and marshlands. At maximum glaciation, where the ocean shore is now, there was a cold prairie occupied by woolly mammoths. The growth of ice sheets lowered sea level, and you could walk from Long Island to Martha's Vineyard, roughly 70 miles. And that landscape formed repeatedly going back close to 2 million years with the advance and retreat of older glaciers. Let's stay on the East Coast. 80 million years ago, dinosaurs roamed throughout New England. The climate was warmer and sea level was higher. Sharks, 3 and 4 times the size of today's great white sharks, swam over what is now Maryland and Delaware. It was a time of intense volcanism and active separation of continents as the eastern part of North America pulled away from Europe. Pieces of a former mountain range were ripped apart. This left Nova Scotia, Scotland, and parts of Scandinavia strewn across the North Atlantic Ocean like a broken necklace of mountains. Let's go further back. 230 million years ago, the Appalachian Mountains formed as the North American and African and European plates collided. Those mountains would have been higher than Mount Everest today. They would have created havoc with weather circulation patterns, and vast deserts formed, and the planet had the greatest extinction event ever. Before that, again, the eastern United States would have been warm, but underwater. In fact, most of the US was underwater about 300 million years ago. Beautiful blue seas like the Caribbean today would have been home to remarkably diverse sea creatures that left behind ancient coral reefs. Rocks like this coral are the rocks we now use as building stone, to make cement, and to drill into for onshore oil. and new coral is still forming off the Bahamas today. It goes on, and that's just the northeast of the U.S. Every place you stand on this planet has a remarkable and rich history that can be interpreted from the rocks around you. Geology rewards a good imagination, to envision things, to understand geologic history, and to be able to grasp the amazing processes that result in the rocks and landscape around you. You really have to open your mind and your imagination. If you do that, then like John Wesley Powell, all about you will be an interesting geologic record. The book will be open and you will read it as you run.